Hello and welcome back to the second day of technical discussions on operating systems. Today we're going to be talking about systems architecture and structure, continuing this discussion, focusing on the I/O interactions of the system. Now, if you remember, we have the sandwich model on the right where we have our luscious, green, wonderful operating systems, the best part of the sandwich in the center. We have the applications on top, the hardware below. I've joked in previous lectures saying that these are completely boring. Please take that as complete hyperbole. Obviously, these are the parts that most people care about. You care about the physical parts of your system, things that you can kick. You care about the applications because that's what we all interact with. The joke is that the operating system is transparent and actually the thing that people generally don't care about. So please don't take it too seriously. We're going to be looking at the lower part of that interaction between the operating system and the hardware this time because we looked at how the operating system deals with the applications last time. Please see that video if you haven't watched it already. Okay, so the general idea here is that we really need to think about our small little systems, even our cell phones, as a distributed system. And you see the picture for that in the lower right. You have your CPU that's connected via a network to all of these controllers for different peripherals and memory. And that is an approximation of how most of our systems actually look. So now each device you can think of as having a controller specific for that device. So for instance, the physical disks are paired with a disk controller that understands the physics of the disks and how to operate them specifically. Each of these device controllers takes commands from the CPU, and it does so through control registers and buffers. So the idea here is that each of these disk controllers in some way has some registers, much like the registers that we think of as being on the CPU, but specific to that family of peripherals, those disks. And the CPU can in some way, through either instructions, like the in and out instructions, which are privileged instructions, read and write those registers, or through memory mapped interfaces where somehow those disk controllers appear in a region of memory. So the CPU can read and write to those registers to interact with the controllers. And then the controller translates in some way these CPU commands into device actions. So that may be sending or receiving packets for a network, that may be reading or writing sectors for some sort of a disk or an SSD, right? Now, I'm not going to talk about this much in the class, but I know a lot of you have probably heard of device drivers. And device drivers are the types of things that you need to install to allow your operating system to speak the language of a specific device. So for instance, NVIDIA GPU cards require very specific binary blob device drivers. So anybody who have those on Linux is typically accustomed to saying, all right, if I want good performance, I need to speak the language of my NVIDIA GPU graphics processing unit, so therefore I need to install one of these special device drivers. So a device driver is actually just a blob of operating system code. It's software that understands how to specifically talk to the device controller of, in this case, for instance, a GPU. And the overall goal there is essentially almost always to figure out how to transfer data back and forth between the CPU and the device itself, right? So how do they do this? The device driver and the device controller typically speak the same language, which is to say they use a protocol for their communication. Just like socially we have protocols for walking up to each other, shaking hands, exchanging small talk, and then getting to the meat of a conversation, all of these devices have protocols for communication. And these are almost always formed by a sequence of manipulations to those registers on the device controller. So these protocols effectively specify how those buffers on the controllers are modified by the CPU and by the devices themselves, and how the registers on those controllers can be used to make requests from the CPU for instance, moving data into and out of the I/O device from the CPU or from memory. Now, when a CPU accesses one of those device registers, it often effectively waits until the data, the request, the word that it's trying to manipulate gets sent over to the disk controller and is written into the register. This can be relatively slow. So, if we look at the scale of some of these things, we know that a CPU cycle on like a 3 gigahertz, slightly faster than a 3 gigahertz machine, is about 0.3 nanoseconds. Very, very small. Just go back and contemplate a little bit how small a nanosecond is and marvel in humanity that we can operate transistors and abstractions on the scale of 0.3 nanoseconds. L3 cache, which is one of the larger caches on most big desktop systems, it's about 18 nanoseconds to be able to access. Memory, about 135 nanoseconds. So these are the scales of kind of the things on the storage hierarchy that we talked about last class. PCIe, PCI Express, is a protocol for this network that connects the CPU to one of the devices, right? You might know about PCI cards that you kind of plug into your motherboard. That's effectively what these are. And if we want to transfer using PCIe, an extremely fast technology, 128 bytes of data, which is effectively a double word, that takes about 900 nanoseconds. So look at that 900 nanoseconds versus the 135 nanoseconds of memory. It's much, much more expensive than going to memory. And then compare it versus a CPU cycle, and you realize that this is almost a veritable infinity for a CPU, right? So while talking to these device controllers can be a very expensive thing, we want to somehow make sure that the CPU doesn't get slowed down to that speed. USB 3, on the other hand, it's a much kind of more generic protocol that, we can all kind of plug external devices into our machine and they speak USB. That can take upwards of 13 microseconds. So 13,000 nanoseconds, compared again to the 0.3 nanoseconds of a CPU cycle. So we have a little bit of an issue here, and that issue is that our CPUs are very fast. Talking to memory is relatively slow. Talking to the controllers for these things is even slower. And then often, actually talking to the devices themselves from that controller is by far the slowest, right? So the question is, how can we create a system that has these huge disparities between the CPU being very fast and I/O being very, very, very exceedingly slow, right? And the core intuition is that if the CPU has to wait for data, it reads, it loads, and it stores from these device registers on the controllers, byte by byte, then this is exceedingly slow. And quite often, the in and out instructions on x86 are doing lists. So we actually have privileged instructions that operate effectively at the speed of those networks, PCIe or USB. Now, the thing is, we really, really want it to be fast as in the speed of the CPU. So how can we get there? That's effectively what we're going to be talking about for most of the rest of the day. Now I'm going to go into another example of how we think about this. In the purple box on the top, you have kind of the CPU. And the CPU can go between two separate states. At the top, you have the CPU doing useful work, right? This is what running our applications is, right? This is running our spreadsheets, running our browsers, watching cat videos, all of the things that if we couldn't do them, what is the use of a computer, right? The internet was created to be a gigantic cat and dog video propagator, right? If we cannot have our cat and dog videos, what is the point of all of this? So we want to have the CPU going fast, 0.3 nanoseconds, as frequently as possible. And the CPU can transition when it does in instructions into the CPU waiting for data state, right? And on the bottom, I've simplified, we'll make it a little bit more complex later, an I/O device, and that's the blue box. So you see that the I/O device is idle when there's nothing happening there. The CPU hasn't made any requests, and the device doesn't really have anything that it's doing. And it can change between that and a state in which either the device or the device controller is transferring data, right? So let's say that we make an in request. In, again, an ISA instruction for asking the I/O device to do something, right? To transfer something into the CPU. And at that point, when we make the in instruction, it gets transferred over that PCIe or USB network to the device controller, and the device controller now understands that something is being asked of it, so it starts transferring some data from the device itself. After some amount of time, the device has transferred that data into its own local device buffers, and it can return that data. Therefore, the in can kind of return with a byte of data. So then we see at the very top that we have more in instructions. Perhaps the device has transferred multiple bytes in from the device itself, let's say a disk, into the buffers of the device controller. So now we can make multiple in instructions, all of which represent the CPU waiting those 900 nanoseconds to actually get the data back from the I/O device. So you can see that while we're kind of making these 5 in instructions effectively, the CPU is spending almost all of its time going at the speed of either the very, very slow I/O device or the slow-ish speed of the device controller communication. And you can see later we make an out instruction, which is writing out to the I/O device, and the same thing will happen, right? So the thing that I really want everybody to notice here is that we have a lot of slow execution speed going on in the I/O devices, and that slowness is getting translated up to the CPU, therefore making the CPU operate at the speed of the I/O devices itself. The ins are effectively blocking the CPU from doing effective work and making it operate at the speed of the I/O device. So what interrupts do? This motivates interrupts. What interrupts do is they seek to replace this notion of asking for a byte of data, making the first in instruction request, and then wait for effectively 3,000 cycles, right? For effectively 3,000 times the speed of, 3,000 times the speed of actually just doing a cycle's worth of operations. And then after we wait for that long, we can get a byte of data, right? We want to replace that very, very slow operation with asking for a byte, saying that we would like the byte at some point in the future, go back to business, go back to running our applications, doing 3,000 times the amount of useful work at user level running an application, and then when the data is actually available, get a notification that says the byte is ready. Now, this notification is very similar to text messages. Like the human analogy here is text messages. Interrupts are effectively text messages from a device saying, that it essentially has our data, right? So the analogy is that, we're doing our normal life, we're in class, we're trying to learn things, improve ourselves, and then suddenly we get a text message. We're interrupted from what we were doing productive learning, and instead have to look at our text and learn that, something dumb has happened or whatever, right? So that text message interrupts us for what we were doing and requires our attention to attend to something, right? So this is our analogy. We want the CPU to be able to make a request from the I/O device controller, then go back to doing its normal business, and then later get notified that the data is actually available on the device, and then it can read it out without having to wait for all of that time, right? So let's talk a little bit about kind of how interrupts are implemented and some of the complexity, and then we'll come back after we understand that to some of the ideas there. So interrupts effectively transfer control to an interrupt service routine, an ISR. So what it means to transfer control, it effectively means that whatever we're executing at some point in time, let's say some application, we need to save that instruction pointer and usually the stack pointer as well as the location that we were executing when we were interrupted. And then we start executing in the kernel, a kernel-defined handler for that interrupt called an interrupt service routine, right? And how this is typically implemented is that every piece of hardware defines a memory-based data structure that is the interrupt or trap vector. And that includes a number of interrupts for the number of a number of entries for the number of interrupts that are on the system. And often it might have an entry, for instance, for the system call handler as well. And that's how the hardware knows by looking up the entries in this array, which you see on the right, where the handler, where the code for the handler for that specific interrupt or the system call is, right? So we can see here that in the first entry in the interrupt vector and the second entry, we have the network interrupt service routine and the keyboard interrupt service routine, respectively. When an interrupt triggers, it's effectively an I/O device sending an electrical signal to the CPU and saying, please stop what you're doing. I have some information that you requested before. Some data is available that you requested me tell you about previously, right? So that signal effectively tells the CPU that it needs to save that current instruction pointer and stack pointer where we're currently executing, perhaps in user level, and somehow start executing the interrupt service routine. The interrupt service routine usually will save all of the other registers that represent the current execution state of the CPU when it was interrupted, right? After we service that interrupt, the CPU wishes to resume execution where it was previously interrupted. So we're doing something interesting in the system. We get an interrupt that starts executing at the interrupt service routine in the kernel. When that ISR is done executing, it restores all of the registers that were previously active, which has the effect of resuming execution wherever it previously was. So the question is, and I've already somewhat answered this, we have the stack pointer and the instruction pointer that are saved, usually by the hardware routines for triggering an interrupt. What about the other registers? And I kind of already hinted to that, you kind of want to do that in the interrupt service routine, if not within the hardware. Now, there are a number of questions I want you to contemplate. Where are those registers saved? And if we need to start executing the interrupt on some sort of a kernel stack, as we discussed for system calls, how does the CPU know the location of that thing? I'll let you think of that for just a second as Penny stares adorably at you. Okay. Okay, so one intuition, and this is incorrect, one intuition is that whatever stack we happen to be executing on, we can just use that stack for the interrupt execution. So let's look on the right at the picture, or let's look at the code on the bottom here. We see that there is a foo function that calls a bar function, and let's just say this is your interrupt, your application level code that you're executing, right? And while you're in the middle of the bar function, it just so happens fairly randomly that the device decided to trigger the interrupt at this point, right? So what we see on the right is the execution stack for that, where we have foo that called bar, so we have invocation stacks corresponding to both of those, and then we get an interrupt. And we saw that the interrupt saves the instruction pointer, and not listed here, the stack pointer, and the ISR likely saves the rest of the registers as well, so that it knows how to actually restore all of those registers. And then let's say that we start executing the interrupt service routine, continuing to use this same stack. Well, this is a problem. Because if foo and bar were executing in a user-level application, we have the case where the kernel, the ISR defined by the kernel, is now executing on that user-level stack. Now, what happened if user level made its stack very, very small? User level controls all of its memory effectively that's been given to it by the kernel, so it could make its stack very small. What happens if user level defined its stack to be so small that it could not fit the instruction pointer being saved, the registers being saved, and the ISR? Well, now the kernel is going to be trying to execute using that user level stack, and it's going to cause some sort of faults because it cannot actually, there's not enough stack for it to save all of its state. Right? There are many more nefarious things that the user level could do. For instance, user level could allow the kernel to execute, allocate a large enough stack, but then when the kernel returns, user level could look at what computation was done on that stack by the kernel. In essence, all the invocation stacks for the interrupt service routine and any of the kernel logic that was executed are now kind of saved on the stack in some way, right? When we pop off an invocation frame and return from those, the data still stays there. So the user level could actually look at the computations, the local variables that the kernel had in all of its functions. And that might, for instance, threaten the confidentiality of the system. We might be able to get passwords in the system and things like that. So generally, this is a really bad idea. You don't want to reuse the user level stack for kernel computation ever, because you don't want to have to trust the user to effectively do anything correct, right? You set up the user for success by giving it memory to execute in, and then leave it to its own devices. And it might blow up that entire environment and memset all of the memory to 0, or it might do productive computation. You don't want to trust it either way. So let's break up the stack. So we're still executing foo, which calls bar, and we get an interrupt. So we're in the application in the top where we see the mode 1 user level stack, and at that point we get an interrupt. On an architecture like x86, what the hardware will do is it will switch to the kernel stack for you. And to answer that question of how does CPU know the location of the kernel stack, this is typically just stored in a privileged register that only kernel can access. So the kernel knows, the kernel has set up a kernel stack in kernel memory, and when the interrupt happens, it will switch to that stack, and the hardware will actually automatically save the instruction pointer and stack pointer often for you onto that stack. And then you start executing the interrupt service routine, which will save additional registers, the user level registers, except for the stack pointer and stack pointer, because those were already saved by the hardware. So now we're executing on a mode 0 kernel stack. And we've saved all of the user level registers, and we're starting to execute it in ISR. So this is often what we shoot for. Just like we did with system calls, we want to switch to a corresponding kernel level stack that we can trust the kind of memory status of, right? Now, there's another situation that actually raises a totally different question. And that's effectively, what if we were executing in the kernel when an interrupt was triggered? Remember, that interrupt is triggered whenever the device kind of decides that there's an event. So the kernel doesn't actually control when interrupts are triggered. So therefore, we could actually have the interrupt triggered while we were executing in the kernel. So what that means is maybe we were executing at user level at some point, and we made a system call. So what we see in the picture here is a mode 0 kernel level stack where we made a system call. It saved the user level IP, stack pointer, other registers onto the kernel stack, and in this case started executing a system call handling routine. I say ISR here, I apologize. That should be syscall routine, right? And that might call bar, which in this case might be where the interrupt actually happens. So in this case, we've already been executing on the kernel level stack. So it's very much not clear what to do when we receive this other interrupt, right? So often the hardware will be intelligent about this and will effectively say, if we get an interrupt while the CPU is in mode 0 in kernel mode. What it will do is it will actually extend that stack and grow that stack downwards to execute the interrupt handling routine. So what you see here is kind of an evolution of the stack. This is not a separate stack as the picture might lead you to believe. So we take that mode 0 stack that had the system call started executing and system call handling routine here denoted as ISR, I apologize, which then called bar, and then we get the interrupt. And what the hardware will then do is save the instruction pointer and stack pointer that were in the kernel at the time that the interrupt happened. And then the interrupt handling routine, the ISR, the interrupt service routine, will save the rest of the kernel registers and actually conduct the execution of the interrupt service routine. So this is called nested interrupts, where we had a single interrupt that was interrupted by another interrupt. Therefore, they are nested. And often this means that we need to use the kernel stack not just for executing one interrupt, but multiple interrupts. And that's what you see in this picture here. When the inner interrupt returns, it will then return to where the outer interrupt was actually preempted. Okay, so let's see what this looks like using kind of the status diagram that we talked about in the previous slides. Here, instead of making an in instruction at the very start in the upper left, we're going to extend that to be able to make a request for some data. So we request the I/O device to actually make some sort of to get data from its backing device, right? But we don't block waiting for that data. Instead, we await at some point in the future some sort of an interrupt. So now, as you see, the device will go from an idle state when it receives a request into some sort of an I/O device transferring. So here the physical I/O device is trying to transfer data into the buffers of the controller, right? Once that data is available in the buffers of the controller, then the controller will generate the yellow arrow, the text message, the interrupt to stop executing whatever was executing productively on that CPU and cause it to trap to an ISR. So now you see the CPU transitioning from doing useful work in the application down to executing in an ISR. At that point, it knows the data is available on the device controller's buffers, and it just needs to read it out. So now we execute the 4 in instructions, and in that case, we still do need to wait for that 900 nanoseconds, which is the expensive kind of going over that network on the system to talk to the device controller. But once we do that, we can actually return from the IRQ and continue going on and do useful work, right? And you see on the right, we're just kind of repeating that same pattern again, making a request, waiting for the interrupt, eventually the interrupt handle triggers. We execute the ISR, which executes the in instructions, and then eventually we'll go back to doing useful work, right? So I want to compare this to the previous diagram. What you see here are the purple lines are effectively where the CPU was before we implemented interrupts. So what you see here is when we made that in request, that was effectively an in instruction and converted the CPU from doing useful work down to waiting for data. Right? So at that point, it was doing nothing useful. It was not doing any useful work in the applications. It was just waiting for the I/O device. What interrupts have allowed us to do is take all of that purple space, the purple outline space, and kind of get rid of all the overhead for that on the CPU. So now the CPU is able to execute in parallel to the device instead of waiting for the device, right? However, of course, when we actually get the notification there's data available, yeah, we need to trap to the ISR and start, reading in the data. So the CPU is still not doing useful work all the time, right? So there may be some more improvements to be had. And to get rid of a lot of this overhead of the CPU effectively waiting for data, talking over the bus, reading word by word from the device controller, to get rid of that we need one additional technique called direct memory access, or DMA. So DMA is the basic idea that we want to create a set of data structures that actually exist in normal memory, normal CPU accessible memory. We want to make a set of data structures that can both be accessed by the operating system in normal CPU memory and by the devices themselves. And the point of this memory is that the CPU can set up large buffers in memory before requesting the I/O from the device controller, and ask the device controller, instead of transferring it into its own buffers to be read out byte by byte later by the CPU, instead of that, for the device controller to transfer that data itself into the buffers that were set up by the CPU. This is called direct memory access because now the device controller itself is transferring data from that physical device directly into the memory that the CPU can access. So now the CPU no longer has to transfer from a device controller because the data will already be in its own memory, right? Once that data has been transferred from the device into memory, then the device controller will raise an interrupt that the CPU can then retrieve, and hopefully it can track where the data is in memory and just access it directly as we access anything from memory via loads and stores. So this gets rid of that overhead of all the ins instructions waiting for that 900 nanoseconds of going over the network on your system to talk to the device controller. So the device controller now needs to be a little bit more intelligent. One of the big trade-offs here is that device controllers are made more complicated because they don't just have buffers to store device data, they also need to understand memory, and they need to understand ring buffers, which are kind of drawn in the upper right here, which I'll spend a lot of time explaining. One question that I want you to think about now is simply, what if the transferred data is always a single byte? So if, in our previous example, we did 4 ins, so we were getting 4 bytes worth of data, maybe DMA makes a lot of sense because you can transfer all 4 of those bytes at once into memory. But what if the transfer data is always a byte? I want you to think a little bit about what the trade-off is there and whether it pays off, and we'll get into that a little bit later. Okay, so we need some sort of data structure to orchestrate this collaboration between the device controller and the CPU. And that is a DMA ring. I drew it in the previous slide as literally a ring, right? A circular buffer, as we call it. Now I want to actually give you the intuition about what the real data structure is so that there's no magic there. So it's just an array. Like when we say a ring buffer or a circular buffer, these are all complicated ways to say, hey, it's an array, right? This array, for simplicity here, has n items in it, right? So it's an array of size n. And if we're iterating through the array, as you can see we have been with the upper arrow here, and we're on that last item in the array, we're on the n-1th item, and we iterate up to the nth item, in a DMA ring or in a ring buffer, it just wraps around, right? So all that this is saying is that we follow modular arithmetic when we're actually incrementing through the ring. So this is why we call it a circular ring buffer, because this arrow essentially circles around the array again and again as we increment through it. Right? So I'm going to draw it in many of these slides as an actual circle, but keep in mind that the actual data structure is very simple. It's just this. It's just a array, right? Okay, so what does a ring buffer do? It acts as the data structure to coordinate between a device controller and the CPU, and the way that it does that is by containing pointers to the memory for the device controller to transfer data into. So what we see here is that there are actually 2 pointers at the top that the CPU maintains. These are just kind of pointers, or I guess indices into the array. We have a tail, which is the furthest away allocated piece of memory, and we have the head that is the most recently allocated piece of memory. So you can see here we have 3 data items in the ring buffer that have been allocated, and you see those arrows going out below to the gray nodes. Those gray nodes are the actual memory that we want the device to transfer data into. So you can see between the head and the tail, we have these populated pieces of memory that are just allocated, usually with like the equivalent of malloc, that we're asking the device to transfer into. The device with the big arrow from the bottom maintains a tail pointer, which is when the device wants to transfer data into the memory of the CPU. When the CPU requests that data be transferred, it's going to start transferring data into the buffer pointed to by the index that this tail points to, right? So if the CPU wants to add memory to be transferred in the future from the device, it simply increments the head and adds more memory into the ring buffer. If the CPU requests data be transferred from the device into memory using this ring buffer, then the device will look at the entry that it's pointing to at the tail and transfer memory into there, and it will do this multiple times as it gets more and more requests for data. So you can see here, the device has now populated 2 of those regions of memory with data from the device, and the CPU, which had previously allocated 5 pieces of memory that were unused and ready for the device to transfer into, now has 3 that are empty and ready to transfer into, and 2 that now hold data. Notice that the tail pointer for the CPU points to the first data that was transferred from the device, which is very nice. Yeah. Once the CPU then wants to actually gets an interrupt from the device that says, hey, I've transferred data into you, it can now dequeue one of those data items from where its tail was pointing, and can say, okay, I know that you transferred some data as indicated by the black node. I'm going to dequeue that off of the queue, increment my tail up, get that pointer to the data that the device has transferred, and eat up the data and do whatever it needs to do. If it's a packet, send it up to the networking stack for processing. If it's a sector from some sort of a persistent data device like a disk or an SSD, pass it up to a file system, right? So there we actually process on the data. So hopefully this is clear in this representation. I'm going to show another representation just for those of you who are visual learners and like to see different ways to represent the same thing. Now we have the same thing where we have the device tail pointer, we have a CPU tail and a CPU head, and the CPU has populated 2 regions of memory for the device to transfer into, right? In between its tail and its head. Now, when the device gets data and wants to move it into memory, so we get actual data from the network, for instance, and we want to transfer it into memory using our direct memory access, we know that we can use the device tail to do so, and we transfer the data into the black memory and increment our device tail, right? So effectively, the device can know where the memory is to put data, copy the data into it, and then increment its tail so that it'll use the next region in memory since that previous one is now populated by it, right? So what does the CPU do? Well, if the CPU wants to get data that was transferred from the device, we can see the CPU dequeue operation here that effectively looks at its tail. If the tail is less than device tail, then it will get the data, in this case red, and turning it to red memory, which is being processed. Again, doing something tasty with the data, right? If the CPU says, oh, you know what, I think that I'm going to make some requests from the device in the future, I need to make sure to populate more memory for it to DMA into, it can allocate memory, purple memory here, and in-queue it by incrementing its head and putting that position in the circular ring buffer to point to that new memory. And you can see that this kind of keeps going around and around. The CPU allocates more memory, more slots, the device uses more of that memory for transfer, and this keeps going around and around infinitely, and this is why we use a ring buffer. So let's go back to our representation that we had before of the CPU and the I/O device in different states. So here, the blue regions are the previous regions that used interrupts, but that use interrupts but did not use DMA, right? So now what we're doing is the CPU in-queues memory, it allocates memory, writes it into the ring buffer so that the device can use it. And you see that as the brown node here. It then requests I/O from the actual device itself that then transitions into a transferring state, right? So now the I/O device is actually trying to get data and transfer it. However, when it transfers data, it copies it directly into that memory that was in-queued previously into the ring buffer, the DMA ring buffer, right? And after it finishes copying it, it knows that the data is available for consumption by the CPU, and it triggers the interrupt. The interrupt triggers the ISR execution within the CPU, which you see the transition for there. And the CPU, instead of needing to do a whole bunch of in instructions and pay the penalty of that expensive network, for instance, PCIe or USB, will just dequeue from the ring buffer, and it already knows that the data that it's looking for is in memory, right? So you can see on the right kind of this whole phase transition just happening again using the DMA ring buffers to directly pass memory. So now what you see is that the CPU is doing almost entirely useful work and is just taking a break from application processing to handle the ISR and get the data from the device. But it no longer needs to transfer any of that data from the device itself, instead offloading that work to the DMA facilities of the device controller itself. And the blue region, again, once we use DMA and don't need to transfer that data via subsequent instructions to transfer data byte at a time, you can see that blue region is essentially all of the CPU time that we're saving to be able to do useful work, right? So now we're just down to the black line, which is a small little dip from doing almost entirely useful work by combining interrupts and DMA. That is the overall goal of interrupts in DMA, to effectively let the CPU execute at CPU speed and never really have to wait for the I/O and slow down to that glacially slow I/O speed. Now, there are some subtleties here. The keyboard device does not actually cause that many interrupts. One of the former students of this class, who I'd been working with since he was a freshman, is by far the fastest typist I've ever seen. And I'm pretty confident that despite how quickly he can press keys, he is not anywhere near on the same order of magnitude of the arrival of network packets over your network, right? Keyboards are inherently very infrequent device. Data is not available on a keyboard that often. So let's say that you have a keyboard, and let's say that you are an amazingly fast typist and you can press 100 keys per second, right? If we're using interrupts to inform the CPU of that I/O, that's 100 interrupts per second, right? Let's assume all ISRs take time to execute, right? They are code. They aren't free. All code takes time to execute. So ISRs, interrupt service routines, do have an overhead. And let's just assume that that's 1 microsecond in this concocted system. That's not super realistic, but it's also, I mean, it is the order of magnitude of a lot of ISRs. So 1 microsecond is 1/10,000th of a CPU. That's 1/10,000th of the CPU time. Sorry. 100 interrupts per second, each executing 1 microsecond, is 1/10,000th of the CPU, right? So that is 1/10,000th of the CPU spent executing interrupts. That's nothing, right? That's not going to result in an appreciable slowdown in any cat videos that you're watching. And if it doesn't impact cat videos, who cares, right? However, if you have a networking card on your system and it executes at 10 gigabits per second, well, a gigabit is a lot of data, and especially for small packets, 64 byte packets, for instance, you can imagine how many 64 byte packets go into 10 gigabits. It's an immense amount. And if every single one of those interrupts was actually, every single one of those packets that was arriving is actually causing an interrupt in the system, and each of those interrupts took a microsecond to execute, what happens is that you are spending 100% of the CPU executing interrupts. When you finish executing one interrupt, immediately following, the next interrupt is ready to execute. So your CPU is not doing any useful work. It's only receiving notifications about the data that was transferred, right? This is called live lock. This is a situation where your system appears locked up because it's not doing anything useful, but it's alive. It's doing a lot of work, right? This is called live lock, and something that systems typically want to avoid. So there's a trade-off between what's called polling versus interrupts. We saw that interrupts are not always the best thing in the system in the previous slide. And polling is usually the other alternative. Polling is just actively checking frequently or periodically whether the I/O device has some data. So instead of using interrupts and allowing the device to tell us when there's data, periodically we ask it if there's data, right? So the kernel repeatedly checks the status of I/O. This usually means reading a device control register, which is that 900 nanoseconds worth of overhead, right? It's not always cheap. And if that device has an I/O request that has finished and likely was transferred using DMA into the CPU, then we can process it. And there might be many pieces of data available if we have many different buffers that have been filled in the DMA Ring buffer from the device, right? So now, instead of getting the interrupt, we're checking periodically, right? If some I/O has computed, we have packets, then we read the memory for it. Otherwise, we go on and continue executing the application, right? Now, this is good. This is good because polling now takes up a constant and fixed overhead. We're doing it periodically, let's say 100 times a second, and if every time we poll we have that 900 nanoseconds of overhead, again we're back down to 900 nanoseconds times 100 times a second is a very, very small overhead for a CPU to actually have to deal with, right? And every time that we do poll to get data, we can retrieve many pieces of data from the I/O device because DMA allows us to queue up many pieces of data from the DMA Ring buffers. So we've gone from a situation where we're getting too many interrupts and it's resulting in live lock into a situation where all of a sudden we can make progress in the system again. So in this case, polling is drastically better, right? But the frequency of polling impacts the latency and throughput of I/O. So latency is the notion that there is a delay between two things, right? And the latency is that delay. So a latency for I/O is a delay between, let's say, when a packet arrives on a networking device and when the OS actually knows that data is available and it has access to the data. So the latency of handling that packet is the difference between those two items. If we use interrupts, the latency for that is very, very low. However, if we use polling, it actually depends. It's a little complicated. If we poll, let's use an extreme example. Sometimes understanding these things is easiest done when you pick extreme examples. So if we poll once a second, right? What is the latency we are going to experience to actually process one of the packets received? Well, in the worst case, a packet is received by the device and transferred into memory using DMA immediately after polling happens. So we have to wait for the next polling period a second into the future to actually notice that the packet arrived. So the latency for handling that packet is a whole second, right? On average, if packets are received uniformly throughout time, then the average latency will be half a second to be able to process any of the packets, right? However, if we choose a polling frequency of 1,000 times a second every millisecond, then the worst case polling latency is a millisecond, and the average case is half a millisecond. So you can see how frequently we poll impacts the latency for actually receiving packets. But it also impacts the frequency of polling, which has an overhead. So the more we poll, the more that polling takes up overhead on the CPU, therefore decreasing the throughput of the system, right? So this question here, I think we've been over it. Is polling ever better than interrupts? Absolutely. In the case where live lock can happen, polling can be better than interrupts, right? In many cases, interrupts are vastly better because they have much better latency properties. But when you start receiving too many interrupts, that is no longer true. So let me give you a kind of concrete in-person example of this. Let's assume that there's office hours, right? Let's assume office hours in a normal year, not a remote COVID year, right? So literally office hours are in an office. There's one professor, often multiple students that want to talk to that professor. And if the professor is giving some sort of an explanation to a group of students, let's assume that that takes about 10 minutes, right, per group of students. Now, the professor can have two policies. They can say, okay, students have to knock on the door when they come to office hours, and I can tell them to wait until the next group, or I can tell them to come in, right? And unfortunately, whenever a student knocks, the professor has to get up, and if they're old or, just clumsy like me, and I'm probably going to fall 5 times before I reach the door, it's going to take about a minute to get up, go to the door, tell somebody to wait, tell them to come in, whatever, right? So every time that we get an interrupt, it takes 1 minute to process that interrupt, right? The other side of it is we can have students wait outside. So do not knock on my door. I am the antisocial professor. I will not have it, right? No notifications. Instead, the professor checks if there are students waiting every 10 minutes. So I set an alarm effectively for every 10 minutes, and I check to see if students are waiting outside, right? Again, I have to get up. I clumsily make my way through my office. Takes a minute to kind of check if people are there, right? So this is the equivalent of interrupts, somebody knocking and saying, oh, hey, I'm here. Can you help me? And the professor polling on their door to see if students are there, right? So let's take 3 examples here to show that the trade-offs that are inherent in this system. Whenever I ask what is the best system, the answer is almost never A or B. The answer is under which situation do you care? Or in this situation, A is better. In this situation, B is better. So let's look at that. What are the trade-offs involved here between A, interrupts, and B, the polling approach? So during normal office hours, I have, half a student an hour. I think that is woefully optimistic. I think that usually there are not that many. Before a test, however, I might get many more students, so 12 students an hour, right? But then, there's that time when I just decided that, everybody should just write an operating system from scratch. And because there's only 2 weeks left in the class, everybody has to do it in 2 weeks, right? So when I did that, that was, my downfall. I got 60 students per hour, right? So that was everybody like, oh my God, is this for real, and how do we do this, right? So everybody had to come to office hours. Now the question is, which of the two policies is best for this, right? So I'm going to let you think about this a little bit, and I want you to consider two different dimensions of the problem. If we want to minimize the amount of time that the professor spends polling or executing interrupts, effectively getting up and walking to the door, what policy is best? Separately, if we want to minimize the amount of time that students spend waiting, i.e. the latency to help students, what is the best policy, right? Okay, takes a little bit of time to think about this. Okay, so we have the two policies again, having a student knock, cause an interrupt, or the professor polling every 10 minutes, okay? So in the case where we have normal office hours, 0.5 students per hour, if we poll, then we're getting up 6 times an hour to check the door, and only 1 out of 12 times a student is there, right? So we're essentially over a 2-hour period spending 12 minutes polling, wasting throughput, wasting our own productivity, our own throughput by getting up and clumsily making our way to the door, and only once is there actually a student there, right? Now, if we get 12 students per hour, so actually, sorry, let me go back. So that's pretty wasteful. Polling is not good in that situation. Contrast that to interrupts, where over a 2-hour period, the one student who comes will trigger an interrupt by knocking on the door, and we waste that 1 minute walking to the door and letting them in, right? So that's not bad. So we spent the 1 minute of ISR overhead effectively handling that one student, as opposed to polling where we waste 12. In a case where we have a pre-test scenario where there are 12 students per hour, what happens then? Well, in that case, assuming that they're uniformly distributed, if we're polling, then every time we poll, every time we go to our door, essentially 2 students will be outdoors. We finish up with the previous students, we let the new students in, and we start the lecture again, right? We start talking again, right? So we are polling and wasting 6 minutes every hour doing that polling, but every time we poll, there are actually students waiting, right? So that's not that bad. That's pretty decent. From a student perspective, how long do you have to wait? Well, from a student's perspective, the professor is polling every 10 minutes. So on average, kind of rounding a little bit, you have to wait for about 5 minutes, right? So the student latency for the polling approach is not that great. If the students use interrupts, then we'll have 12 interrupts an hour, which is 12 minutes spent in the interrupt service routine, i.e. walking to the door to answer the knock, right? So it's double the overhead, again, for interrupts, but the student latency you might think of as being much better, right? Because immediately when a student arrives, they could get let in if that's the policy, if that's what we want to do, right? So the latency is drastically better for interrupts, but the overhead is worse. So this pretest scenario is a case where polling is better if you consider the overhead on the professor, but polling is worse if you consider the latency per student, right? And then let's look at the other extreme where we get nearly infinite students, right? One student coming a minute. Well, if we use interrupts, then we have the horrible live lock scenario where all that we're doing is getting up and answering our door. If we use polling, we have the polling overheads, and every time we let in 10 students to actually discuss the material, right? If it's slightly less dramatic and, well, yeah. Okay, so that's generally the trade-off here. So what we've talked about then is effectively how the operating system interacts with devices, with I/O devices. And we started from a position where the operating system talks over very slow networks to the device controllers, and therefore the CPU gets slowed down to the speed of those device controllers, and in the worst case, the devices themselves. We added interrupts that said, well, you know what, this polling is expensive, where we just kind of keep asking for data and then waiting for it, right? So what we want is really interrupt so that you can notify us when data is available. And only then will we actually do some processing, right? And then we wanted to say, well, okay, but once data is available and we know it's available and in device controller buffers, then we need to manually kind of read it out byte at a time from the CPU. And that's very slow because every time we read a byte, it goes over that network speed, 900 nanoseconds for PCIe, right? So that's not good. So let's use DMA, direct memory access, to have the devices transfer the data themselves. The sum total of all of these techniques is that the CPU itself can run at its native and fast speed, and the devices are given some intelligence to be able to effectively transfer their data directly into memory, or, I didn't really talk about it here, get data directly from memory. And notify the CPU when the actual data is available. So that is all for today. Hope you had a good one.